Now, of course, we will assume that, of course, the more accurate calculation actually is not from the ground. So let me correct it. Okay? So this 2 meter is from the bottom of the door. This way we will be more precise. So 2 meters is actually the length of the door. This way, the center of gravity is just 1 meter below the point A. That means the garage door is like this. From here to here, this is point A, and at the bottom is point B. What I meant is the whole thing. The garage door has a 2 meter length, like that. And the center of gravity, of course, is at here. So the mass is right at this point. Now, the first thing we want to do is, of course, always to determine the required properties. We want to know what's the mass moment of inertia. So the first thing is to find out the mass moment of inertia. Now, remember, you do not want to use the mass moment of inertia at the center of gravity. You want to use the mass moment of inertia at where? At the center of rotation. Because if you do it, you can ignore the linear component. If you use the mass moment of inertia at the center of gravity, you have to consider two terms, Ig and also the linear velocity. And in this case, you know the linear velocity keeps changing its direction. So it's not a good idea to use Ig. It's always a good idea to use Ia, or I at the center of rotation. So find out what is Ia, and you can use two different approaches. If you remember the formula, which is 1/3 of total mass times total length squared. This way we model this garage door like a slender bar. This is one approach. Or if you don't remember this, you use what we call parallel axis theory, right? From parallel axis theory, you remember at the center of gravity is 1/12 of mass times L squared plus md squared, total mass times d. D is half of the L, so it is L over 2 squared. And either way, you're going to get the same value. So if you remember for a slender bar, at the end of the slender bar, the mass moment of inertia is 1/3. Then you can just copy this one. You don't have to use parallel axis theory. If you don't remember this, you use this, but the result is going to be the same. Okay? So we just calculate 1/3. The mass is 25 kilograms. The length is 2 meters. And this will give us the value of 26 point. What did I do wrong? Oh, I'm sorry. The mass is 20 kilograms, not 25. Please correct it. This is 20. So this will give us 26.67 kilogram meter squared. So this is the mass moment of inertia. So this is 20, not 25. So we have this found. Now, secondly, we're going to plug everything into the conservation of angular impulse and momentum. From the conservation of the angular impulse and momentum, we know from T1 to T2, there is moment, dt equals to mass times, not mass, this is the mass moment of inertia, Ia times omega 2 minus Ia times omega 1. So here we have to be careful. There are, how many time instances do we have here? We actually have 3 time instances. The first one is before the car or the garage door starts exhibiting any velocity. That's at the moment when the car hits the door. That is the transition from angular momentum to here, angular velocity. Which means in this formulation, the first thing you want to figure out is what is the angular velocity at the moment when the car has been hit. So the initial velocity, of course, is going to be 0 because before the car hits the door, there's no velocity. of the garage door. Of course, omega 1 is going to be 0. So the first formulation is actually to figure out what is the initial angular velocity of the door. That's what we're going to figure out. And then you carry this linear and this angular velocity to what? To principle of work and energy. Because in order for the door to move from the vertical position and swings up to 150 degrees, you notice that the center of gravity has been moved from this position to somewhere here, correct? What does that tell you? That tells you that in order for the door to move, it must use its kinetic energy to consume potential energy. Because when the thing goes up, you will have to convert kinetic energy into potential energy. So what we know the final condition is, if this is the maximum angle, that means at this point, there's no kinetic energy. That means the door stops moving. So at the beginning, the door has an initial velocity, something with omega 2, and moves up to here and stops. That means at this point is the maximum potential energy and 0 kinetic energy. At this point, the vertical orientation is 0 potential energy, but maximum kinetic energy. So this conversion is from T2 to T3. So we're going to define this moment as T3, where you also define the position. For what? For the calculation of potential energy. And when we do this, certainly you want to define the original position of the garage door as what? That's what we call the datum line. So you're going to define the datum line at T2. You're going to do it this way. And if you do this, you will know that after the impact, this is datum line. And after impact, it's going to move to here. Correct? And because it's 150, so we know that what's this angle here? 60. Correct? And we also know the length of the door, which is 2 meters. So you know that this is 2 meters. But what we know in calculating the change of potential energy is from this point to this point. Correct? Now you know this whole thing is 1, so you can actually just treat this whole thing like 1 meter length. So the 1 meter here and most up to here is 1 meter. So what is this total length? The total length here, clearly this part is just 1 meter. Right? What about this part? It's 1 meter times, is it sine or cosine? Sine or cosine? If you use 60, of course, because there's 30, there's 60 here. Sine, right? So this is 1 meter times sine 60 degrees. And this will be the change of potential energy. From this point moves up to here. You will need to know this distance is. Now, of course, sine 60 is what? Sine 60 is 0.861. So you can actually calculate that means 1 meter times 0.61. That means this whole thing is 1.861. So we know this whole thing is 1.861 meters. There we go. Then we pretty much have everything we need. So you just plug in here, coming back to principle of angular momentum, impulse and momentum. What is the moment A here? The moment A is the force times force arm. And the force arm is what? We describe it here is 0.25 meters from below. So that means it's 2 minus 0.25. which means this moment is just from T2, it's just the force times 1.75. Correct? That's the moment. Force times force on times dt. Correct? And this equals to what? Equals to IA, and we already find out the value of IA. And this IA is 26.67 times omega 2. And omega 1, of course, 0, because it starts from the rest. Now, before you carry out this integral, remember the problem asks you what is the linear impulse. So you may want to write the left-hand side as this. 1.75 is a constant, you take this thing out, so you can write this to be 1.75, and the rest is actually the expression of I122, right? Because 1.75 is constant, you can take it out of the integral, and the remaining part is exactly what the problem asks you to determine. So the remaining is just I122, and you're going to write this equals to 26.67 times omega 2. Okay, so this is going to be our first condition.